assistant at Dalhousie University, specializing in geotechnical engineering. Research focus on microbial, biofoundation, soil improvement techniques, finite element modeling, AI application, and so on. So go ahead, Dr. Ahmed.
Yeah. So good day, everybody. And first of all, I'd like to thank Dr. Mahmoud for inviting me and giving me the opportunity here for a second time in Ramadan to give a presentation about my research done here at Dalhousie University. So this research is about large span soil steel bridges, and it's done under the supervision of Professor Hani El-Nagara and Professor John Newhook. And today I'm going to talk about like the finite element modeling of these structures, and how to see and how to evaluate the effect of the soil model employed in the Plaxis software, for example, on the response under soil loading and truck loading. So the outline here, the main content of this presentation, I'll start with a quick introduction. I would like to let you know more about this structure, this composite structure, and then I'll move to how we validated the accuracy of our model, finite element model, and then I'll show you what we have done here to evaluate the soil model effect. Moving to results and discussions, and I will end my presentation with the main conclusions. Okay, so first of all, if you are still wondering what's the meaning of a soil steel bridge, here it is. That's a picture for one of these structures here in Canada during the construction process. And as you see here, you have a corrugated steel profile that can take many shapes, but here I'm talking about an R shape. And you can see that this structure is considered an underground structure or a buried structure, because after placing the corrugation profile, which takes the shape of rings, and bolting them together next to each other, you will backfill the whole structure, just like the cut and cover technique in tunnels. This, what we have after the end of the construction, here this bridge is used as a wildlife crossing so that animals can cross the highway. And here, some other pictures. On the left, we have, so far, this one is considered the largest span soil steel bridge. And as a span here, I'm talking about the distance between the spring lines from here to here, from this edge to this edge. This is called the span of the soil steel bridge. Here you can see here the span is 25.74 meters. So about 20 years ago, our largest soil steel bridge in our real world was about 10 meters or 11 meters. But right now, due to the advancement in the construction and due to the advancement in the industry, we can see spans reaching up to 32 meters. This one here on the left, that's the largest span soil steel bridge. It's in Dubai in the Middle East. It has a span of 32.4 meters. And this one, that's the second largest span. It's in Poland in Europe, constructed in 2017 in 25.74 with a span of 25.74 meters. If you are wondering, maybe these structures are relatively new. They are constructed like 4 or 5 years ago and 8 or 9 years ago. That's of course because the structure itself, this corrugation profile, was only developed and available in market since 2011. So it's available, it has been available in the market only since 2011. So it's a new material used in the construction of these structures. Okay, so the typical construction method, because that's very important, because you have to consider as like a very complex construction sequence in finite element modeling to mimic the real performance. So you have to consider, if you have excavation, you have to do the excavation something like this here. And then you have to construct, or you can construct your reinforced concrete foundation. Most of the time it's strip foundations. In some cases they are constructed on piles. And you have your corrugated profile, which can be explicitly modeled in softwares. But I'll show you later that we can simplify these corrugations by assuming what's called orthotropic parameters for the steel. You may see here that we have like a base plate which connects the steel profile with the reinforced concrete foundations. Moving forward, we have here the backfilling process, which is very, very critical for this type of structures. It can control the design. And you see here, I have my backfill on the right-hand side and on the left-hand side. And then after completing the full construction process, you will have something like this. And this distance here, it's called the soil cover over the crown of your structure. And it's important. This soil cover here, this distance, the vertical distance between the surface and the crown of your structure, this soil cover can govern the design against live loads, which comes from moving vehicles and trucks or trains. So during this construction process, it's very important to consider what's called balanced or symmetrical backfilling. You put and you apply the backfilling on the left-hand side and on the right-hand side equally, with equal compaction efforts and equal thicknesses. And during this construction process, the crown, since you don't have any reaction from above, the crown will peak upwards. However, if there is no balanced backfilling, something like this here, if the left-hand side, for example, has a higher backfill than the right-hand side, or you applied here a higher compaction effort, you will get some rolling in the deformed shape of your arch culvert, which is not preferable here. That's not recommended. That's a very big problem in the construction process. Okay, I told you like 2 or 3 slides ago that what helped us to construct these structures is the material of the steel. You have here deep corrugation profile. That's the corrugation we are using. That's called deep corrugation profile, and this name is according to the Canadian Highway Bridge Design Code. So I will adhere in my presentation to the Canadian manual. So here it has a wavelength of 381 millimeter, thickness of 140 millimeters, and that's our hero. The deeper corrugation profile developed only in 2011, and it has a wavelength of 0.5 meter and a depth of 237 millimeters. Very high rigidity and high resistance to bending moments, thrusts, and deformations. So before going deep into my presentation, the last piece of cake here in my introduction is the soil models that we can use in Plaxis. So here you can see that we have 3 popular material models: Morclone model, hardening soil model, and hardening soil with a small strain stiffness model. I just want to give in 1 minute or 2 minutes a quick introduction to the main basics that may affect our model. The Morclone model is very well known, and it features a bilinear stress strain curve. The main problem in this Morclone model is that it only considers one stiffness, and the second problem, it doesn't develop any plastic strains unless you reach the yield or the failure line. So if the soil is still elastic and you are applying compaction effort in the finite element model, once you remove the compaction load, the elastic strain will be completely reversed and you will lose the strains you have in the soil. That's a big problem because we want to simulate the compaction process in the finite element model. In the hardening soil model, we have an advanced model here, nonlinear stress strain curve with 3 types of stiffness moduli defined and assigned to the plexus, including E50, E unloading, reloading, and E odometer. And if you remember 2 slides or 3 slides ago, I told you about the cut and cover technique. And here the E unloading, reloading value will play a major role in controlling the deformations, which we don't have in the Moore-Coulomb model. HSS model, hardening soil model with a small strain stiffness, it's an advanced model of the HS model, but with the incorporation of the large shear modulus at very small strains, which is something we would like to have again in when applying and removing the compaction effort. Why is this topic important? Because in my research and my PhD, we are going to investigate these large spans. And the Canadian manual is not giving any recommendations for these large spans because they are relatively new. So it's only recommending that if you are going further than 10 or 11 meters span, you need to do refined analysis, which is meaning that you have to do finite element or finite difference. So if you don't have any way, and if you must do finite element modeling, so we have to see which is the best model that can be employed to simulate the behavior of the soil. Okay, so let's see what we have done to validate the accuracy of our numerical model. We have used the experimental test done by Lurid in 2008 in Queen's University. That was the experimental setup. This is a very good test because it has we can call it a medium span right now. Nowadays, 10 meters is a medium span, but 20 years ago, that was a very large span. Okay, so that's a good span. We have the rise of our structure the rise is 2.4 meters. The soil cover was 45 centimeters. And we have like a live load here. I am simulating here E1 test. So we have here a point load. You have all required dimensions here. They are given. And since there is symmetry in one plane, we have considered this and we have built only 1/2 of the complete structure. This is a point load, but as I told you, we have actually it's a single axle beam having 2 point loads on 2 steel plates. So we only are simulating here 1 point load because we are having we are modeling only 1/2 of the structure. And to simulate the construction process of this bridge and in the parametric study as well, we have used the action compaction approach, which is proposed in detail, let's say in detail, by Ezzeldin and El-Naggar, and it was tested and verified against against field tests in 2022. So what's the compaction approach about? Let's see. So the action compaction approach starts with placing our backfill on both sides to have balanced backfilling, but in a loose state. Loose state means small stiffness and low friction angle. And then in the same phase, remember to put your compaction efforts. We are simulating the compaction effort here as a surface surcharge of a value of 15 kPa. And this value was calibrated against a number of field tests. And it has been tested and verified that it's reliable to simulate the effect of the compaction machines going forth and back for a number of times to compact the soil. And then in the second and in the subsequent phase, the loose, the first layer, which is 30 centimeter in thick, by the way, it's 30 centimeter thick, so it's changed to dense state, and then you have placed here a new soil layer, again in the loose state, and the corresponding surface surcharge. And as you see here, this process will be repeated until you reach the desired level or the desired soil cover over the crown. To, if you want to, you can have, if you see here, there are some loads here which are simulating the truck loads. Okay, so again, let's get back to Lurid in Queen's University. The experimental tests, these are the parameters for the loose backfill and the compacted backfill. Just a little remark here that if you see the E unloading reloading given to the loose backfill, we have used the same value as an E50 for the compacted backfill, because it's the same material, but that's in the loose state. So when doing reloading, this 60 are going to be this, or the E50 for the compacted backfill. For the corrugation profile, I told you that if you want to explicitly model the corrugation in Plaxis, it's doable, but it will take much time and lots of meshing problems may happen, specifically for large spans and long, for large spans and large structures, and even for something we called bevel-ended treatments. Anyway, so if you don't want to explicitly model the corrugation and you want to simplify the problem, you can use an equivalent plate which has an equivalent thickness, but you must consider new parameters for the steel, because the stiffness in the circumferential direction must be higher than the stiffness in the axial direction. So if you want more details about this, you can see the equations that we have used to get these parameters. It's based on the work done by a professor in Australia, and it has been used and verified by lots of researchers, out of whom is Wadi Elshimi and just mine. I don't remember other than Wadi and Shimi right now. We have considered the geometric nonlinearity of the problem during the finite element modeling. That's something which is called updated mesh option, and it's in Plaxis. Okay, so these are the results of the validation process. It's just one test of many tests we have used to validate the model. That's one of them, and it has been published. That's why I'm showing it here. That's the relationship between the force applied live force and the displacement of the crown just beneath the load. You can see a perfect match between the experimental results and the numerical results. And in the steel arch, along the steel arch, if we have here the unfolded distance on the x-axis and the bending moment on y-axis, or the axial thrust, which is the normal force in the circumferential direction, you can see that we have a good agreement as well. So we are a bit sure now that we are a bit sure that our model now is doing well, and we can start our study. So in the parametric study, we have expanded the span to 18.1 meters, and actually in my research, I have investigated a span of 25.5 and a span of 32.4, But here I'm presenting the span of 18.1 meter only. We have done the construction process as I have shown you. And for the life loads, we have a truck here moving in this direction across the soil steel bridge. So it will look like this. These are the truck loads. It's a CL 625. That's the full truck load specified in the Canadian code. And these are the loads and the geometry of the truck. And again, we are just simulating 1/2 of the bridge, which is we assuming here that this bridge is have a width of 6 meters. So 1/2 would mean that we have a width of 3 meters in plexus. We are not considering doing any influence line here, or we are not simulating moving loads in plexus. It's just one static load. We are placing the truck such that this point, it's called the center of this tandem axle. So this point, it's gonna be placed here over the crown. This would have the largest effect on the structure if you want to consider the life load design. Okay, for the parametric study, we have, as you see here, we are not applying any fixed boundaries at the soil arch or at the base of the soil arch. The base is here, the base of the model. So we have here, this is called natural soil or the native soil, and this is a backfill soil. The natural soil will affect, of course, the design of the foundations, and the backfill soil has a direct impact on the structure. So these are the parameters of the natural soil, the backfill in the loose state, the backfill in the dense state across the 3 models, MC, HS, and HSS. And here we are using one of the deeper corrugated profiles, which has a wavelength of 1/2 meter. And these are the orthotropic parameters, which are based, again, as I told you, upon the equations proposed in around 1980. Okay, so going into the results, before presenting the results, I would like to show you here, these are mostly, they are the governing phases during the construction, these two. This one is called the peaking phase, and it's called peaking because I told you that this crown is peaking upwards during the construction and compacting the backfill. This one is called the full dead load. That's when you have reached the full soil cover. And this one is called, maybe you may call it life load or final phase. I have called it here final phase. And here are the truck loads. Okay, so as many of you may expect, when you look at the deformation of the foundations, the more column model, we have here the value of the movement. We have here the vertical movement, differential settlement at each footing, lateral movement of each footing, as you see here, lateral movement and vertical movement. Okay, so the more column, as you may expect, is overestimating the deformations. This one is very high compared to the HS model and HSS model, and that's this is due to the stiffness assigned to the soil, because I told you that in HS and HSS model, these models are using unloading reloading to estimate these deformations, but the more column doesn't have this value. So as you see here, the more column is overestimating the foundation deformations, and if you are a designer for such a structure and you are using more column model because it's a quick and easy model, you will over design and oversize your foundation, because you will get a very high level of movements, especially if you are using the cut and cover technique in constructing this structure. Now let's go back to the arch itself. So the arch itself, as I have shown you, that you will have peaking, the crown will peak upwards when you are while you are backfilling the soil on both sides. So that's what we have here. You have positive deformation. That's the crown deformation. It's taken here as a percentage of the rise, and that's a backfill height. So my rise here was around 5 meters. So as long as you are still backfilling below this level, this line, you will have positive deformation. That's called peaking, because the soil in both sides are pushing laterally the arch, so the arch crown will move upward. After the backfill gets here, and you are now placing and compacting the soil over the crown will take a different behavior and it will deform downwards again. That's what we can see here. So 5 meter, if you are less than 5 meter, you will get a peaking deformation. If you are higher than 5 meters, the crown will start to deform downwards. As you see here, the HS model and HSS model, they are typically giving very close estimates. But the Moore column model, again, being affected by the stiffness values assigned to the soil and being affected by the fact that any strains developed due to the compaction will be reversed again after removing the compaction. So the arch will rebound. Any deformation or much of the deformation, let's say much of the deformation of the arch will rebound after removing the compaction effort. So that's why the Moore column, you can see, I'm telling here that it's underestimating the upward or the peaking deformation, and it's overestimating the downward deformation. And that's a very big problem, especially if you want to compare it with the allowable limit, because the allowable limit in the code is 2% of the rise. We see here that we are not exceeding the limit, 0.7 positive and 0.6 negative, but maybe in a larger span, because this one is 18.1, maybe in a larger span, the Moore column model will give you a value that's exceeding the code, and it's not real. Okay, we have here the global deformed shape for the peaking phase and for the dead load phase. You can see here clearly the peaking I'm telling you about. That's the peaking of the crown. And you can see here that the Moore column model is underestimating the peaking that is taking place at the crown. And the dead load phase, which means that you have constructed the structure completely and you have the full cover over the crown being backfilled and placed in position. So here you can see that the Moore column model, if you are looking in the downward movement, the Moore column model is overestimating the downward movement. And if you look here at the base of the arch, look here at the base. So the base of the arch or the spring line, you can see here that the Moore column model, due to the large downward movement, the base of your arch is also moving downwards a lot more than the HS and the HSS model. So here you can see that even the global deformed shape, not only the crown, but also the global deformed shape is harmfully affected by the adoption of Moore column model. Moving to the effect of the truck load. So here we have, these are the tire loads we have from our truck. This is the tandem axle. I told you that that's the most critical position. You can see here that's the unfolded distance, relationship between the unfolded distance and the vertical deformation along the whole arch. So that's your unfolded distance of the whole arch, and that's a vertical deformation. You can see that again, the problem in the deformation again and again and again, the Moore column model is overestimating the downward movement due to the track loads. There is like some or a quite level of error between the HS and the HSS model, and this is easily contributed to in the incorporation of the large shear modulus at small strains in the HSS model. So the HSS model may be at some strain and some stress levels, it will have a stiffness that's higher than the HS model. Of course, I know that all of you know about this, but just in case, higher stiffness means less deformation. So that's why you see the difference between the three models. Okay, the final results here about the axial thrust, which are used to design the corrugation and to select the corrugation profile. So the axial thrust along the unfolded distance, the HS and the HSS model are giving very close estimates, but the Moore column model is underestimating the thrust force. Underestimation means that you will get less buckling stresses, you will get less axial compressive stresses, and this can deceive you, and this can lead to a wrong design if you take like a lower section in this design. For the bending moment distribution along the unfolded distance, we have here this is a typical shape of bending moment distribution at the final phase after imposing the life loads. If you see here, we have at the middle negative moment, peak negative moment here, and a peak negative moment here, and then you see this like it was going to be a positive moment at the center, because we have here like the large effect of the truck. The large effect of the truck, it's at the center. Like, just assume that you have a simply supported beam, you would have a positive bending moment at the middle due to any point load in the middle. So the construction process and the soil loading gives you a negative moment. So at the beginning, let's see, under construction, it looks like this. But after applying the truck loads, this peak, it wants to move in this direction towards the positive moment. Anyways, so here we have, we are talking more here about the difference between models. So you can see that you don't have much differences here between the three models when you look at the axial thrust and bending moments, but still, if you are doing some value engineering and you want your design to be very specific and very accurate, you still have to consider the HSS model for accuracy of internal forces. Okay, so that's all what we have today in this presentation. To conclude, talking about the footing deformations, the Moore column model can be a disaster. It overestimates the deformations in all directions, vertical, lateral, and even differential settlement. For the deformations along the arch during backfilling, the Moore column model underestimates the upward deformation and overestimates the downward deformation. During the traffic loading, under the truck loads, the Moore column model, it overestimates the crown downward movement. So as you see here from these 3 points, there is a big problem considering the calvar deformations due to the rebound of the structure after removing the compaction in the more column model, and due to the stiffness applied to the soil in the more column model, which is 1/3 of the E unloading reloading that we have in the HSS model. The straining actions and the internal forces, it's not a big deal, but you must consider that the more column model, we have seen that it underestimated the thrust forces. And if you are doing value engineering, you must consider this, especially for buckling considerations, because buckling considerations in large spans is very critical. So that's it for now. So here we have a list of references that you can look at if you want to have more information about these structures. And about my research, this presentation was a part of a major chapter or a major research paper which has already published in Journal of Constructional Steel Research. It's available open access, so you can read it. And I would like at the end to acknowledge the funding that I have received from NSERC of Canada and the Nova Scotia Department of Public Works. And if you have any questions or need any more details, you can just contact me using this email. So at the very end, I'd like again to thank Dr. Mahmoud and thank all of you for your attention, and feel free to reach out to me if you need any or if you have any questions. Thank you.
Thank you very much.